G'day chemistry students, in this video we are looking at dot point 8.2.2. Our focus is going to be learning about how to interpret and use HNMR and Cnmr spectroscopy to identify unknown chemical samples. Let's get into it. So first off, for HNMR, there are a few different things that we can record when looking at the results or a spectra for HNMR. We can look at their Ppm shifts. We were talking about those in a fair amount of detail last lesson. Our splitting patterns we can also use, so they were the different peaks sort of within a peak. I'll get to them shortly. There's also these things called integrals. So we can record all of those and use all of that information to help us identify our unknown sample. So first off, we can use Ppm shifts, these chemical shifts. So the position of each of the peaks may indicate what type of hydrogens are being represented by these nuclear flips that are happening. Generally speaking, this isn't the most useful thing that HNMR is sort of here for, and as a result, we won't find that data in the data sheet. If you ever need to reflect on the chemical shifts that are present in a HNMR graph, then you should be given one of these tables. It's not something that you need to memorize. What I do want to focus on though is this idea of different hydrogen environments. This is going to help us to understand splitting patterns and integrals in a lot more detail. So for example, in this chemical that I've got on the left, there are two hydrogen environments. There's HAs and HBs. Don't necessarily need to use that labeling system, but it can be helpful at times. So for our HAs, this hydrogen is bonded to a carbon, and that carbon is bonded to another hydrogen and a chlorine. And that carbon here is bonded to a carbon bonded to two chlorines and a hydrogen. Now, this hydrogen here has exactly the same bonding setup. It's bonded to a carbon with a hydrogen and a chlorine, and that carbon is bonded to another carbon with two chlorines and a hydrogen. So because this hydrogen and this hydrogen could essentially be interchangeable, we say that they have exactly the same hydrogen environment. But these don't share the same environment as this hydrogen does. This hydrogen is bonded to a carbon which has two chlorines, unlike these hydrogens. And that carbon is bonded to another carbon with two hydrogens and one chlorine. As such, this is one type of hydrogen environment where these two hydrogens are essentially equivalent based on their position and what they're bonded to. And this hydrogen environment is completely different. That idea of what a hydrogen environment is, super important moving forward. In our next example, there are a few different hydrogen environments that we can look at. The first one here includes this hydrogen, this hydrogen, this hydrogen, this one, and this one. They're actually all the same. So if I look at, say, this one here, it's bonded to a carbon and which has two other hydrogens. And that carbon is bonded to a carbon with an alcohol group and a hydrogen and a CH3 on the other side. That's the same for any of these hydrogens. We can say exactly the same thing, but it's also the same for these hydrogens over here as well. So this hydrogen is bonded to a carbon with two hydrogens on it, just like this side. And the carbon is then bonded to a carbon with an alcohol group and a hydrogen, and then a CH3 on the other end, just like the other side. Now, the reason why all of these hydrogen environments are the same comes down to the symmetry that is in the molecule itself. That certainly is an assisting factor. It's not particularly common, but it's certainly possible for hydrogens that belong on different carbons to have the same environment, and that will happen when there's a degree of symmetry there. But there are two other environments that we can look at as well. There is this single hydrogen by itself, which is also different from the hydrogen that is on our alcohol or hydroxyl group. So what that means is in this molecule here for propan 2-ol, there are three different kinds of hydrogen environments present. So now that we know a little bit more about how to what hydrogen environments are and how to identify them, let's look at how we can apply some of this idea to splitting patterns. So we can use a splitting pattern to identify the number of hydrogens bonded to neighboring carbons. And there is this idea of the N+1 rule. When we look at the N+1 rule, what we say is the number of peaks is equal to N, where N is the number of hydrogen neighbors in other environments. That may not make a whole lot of sense, so I'm going to try and explain it using the example that I've given here. If we look at this peak, we've been told that it is connected to this HB environment, and we can see that within the whole peak itself, if we zoom right in, there are actually 3 peaks. The whole peak has been split into 3. That is our splitting pattern here. Now, the n+1 rule dictates that the number of peaks that are here, our 3 peaks, come back to this idea of n+1. That there are 3 peaks because there are 2 hydrogen neighbors that are in other environments, plus an extra peak. In other words, there are 2 neighbors here, and that +1 leads to 3 peaks. So if I look at my neighbors over here, there are 2 hydrogens in a neighboring environment. So 2 + 1 leads to 3, gives us our splitting pattern here with 3 peaks. We also call it a triplet. If we look at the HA environment, it's made of 2 hydrogens. That's completely fine. What we see is that there are 2 peaks. Our peak has been split into 2. By the n+1 rule, the number of hydrogen neighbors in other environments must be 1, because 1 + 1 = 2, a number of peaks. And that makes complete sense because in our HA environment, when we look at neighboring hydrogens, there is only 1 neighbor that is a part of another environment. We don't just get doublets and triplets. We have all sorts of other splitting patterns. We can have quartets, quintets, sextets, and septets, for example. And you will see what we call relative peak intensities, so ratios of heights. The outermost peaks in the splitting pattern will be the smallest, and that can be visualized in this diagram here. So as it says up here, the splitting patterns can be used to identify the number of hydrogens bonded to neighboring carbons, and the number of splits tells us the number of hydrogens bonded to neighboring carbons. A little bit difficult to sort of get your head around and certainly difficult to define, something that we're definitely going to be doing a fair amount of practice on in class. So having a look at this example of a splitting pattern, we have a few different hydrogen environments. We've got one environment here with our CH3 group. All of these hydrogens are essentially equivalent. We have another environment here with the CH2 and a final environment with our hydroxyl group. Now, an extra rule on top of everything else that we've been looking at the moment is that hydrogens separated by oxygens and nitrogens will not interfere with each other and don't actually contribute to splitting. So, for example, if I were looking at my CH2 here and I was to count my neighbors, there would be 1, 2, 3 neighbors present. We would not include this hydrogen because this hydrogen environment in orange is not connected to the hydrogen environment in yellow by another carbon. It's connected by this oxygen. And as such, we do not count it as a neighbor. The reason for which we can maybe discuss a little bit more in class, but for the moment, let's talk about it from a practical standpoint. What this means is if we were to find a peak for our CH2 environment in this ethanol molecule, what we would expect to see is a quartet. So using our n+1 rule, we have 3 neighbors plus 1. We would expect to see 4 peaks. Again, that would be a quartet. So our splitting pattern would look something like this. If we did include this hydrogen, it would be a quintet like we've got on the side. However, we do, again, not count hydrogens which are bonded to oxygens. If we were to look at this hydrogen environment here and try and figure out what the splitting pattern was, it's actually quite simple. There are no neighbors to the yellow hydrogen. Again, reason being that any other hydrogens on the left-hand side of the oxygen are being separated by an oxygen and are not connected by a carbon. As a result, there are no neighbors. So n plus 1 in this case would be 0 plus 1, meaning that there is one peak. And we would expect to see a singlet. Again, this is only the first time that you've been exposed to splitting patterns and how they work. If you're looking at this and it's all still a little bit confusing, come to class, ask some questions, we'll do some practice, and hopefully it will make sense quite quickly. Last thing I want to talk about is integrals, and we can use that to figure out the number of hydrogens which are in the same environment. So integrals, generally speaking from a more mathematical standpoint, indicate the area under a curve. So for us, that's the area underneath each set of peaks. Something to note is that for NMR, we can't just look strictly at the height of a peak. One, because the splitting pattern will spread the area of the peak across a wider range, as well as that some peaks are just wider than others. So it's not just based on height. The integrals are something that are generated by a computer. If you do need to use integrals in your NMR analysis, it will be literally physically drawn onto the graph itself. What we can see here in this NMR example for ethanol is that there are 3 peaks, which is to be expected because we have 1, 2, and 3 hydrogen environments. It has the splitting patterns, just like we looked at in the previous slide. And we also have these integrals here. So it's this S-style shape that shows the integrals. And we can compare these integrals by height. So you literally get a ruler, measure from top to bottom, and then figure out the ratios of each of those heights to determine how big the area under the curve is for each. What we can see here is that we have a 1 to 2 to 3 ratio. What that means is for this peak here, which is a singlet, because for our OH group there are no neighbors, it's separated by an oxygen, that the integral 1 here means 1 to 2 to 3. There is 1 hydrogen present in this environment. When we look at the next peak here, if it's a 2 in the ratio, that means that there are 2 hydrogens present in the environment like we can see. And this 3 here indicates that there are 3 hydrogens present in the environment. So for HNMR, what does it actually tell us? Well, each hydrogen environment is represented by a single signal, and each signal can tell us the number of hydrogens which neighbor the environment, or the splitting pattern, and it can also tell us the ratio of hydrogens in the environment compared to the others, and that is done using our integrals. We can also look at the bonds that are present in the organic chemical, but that's only if we have ppm shift data available to us. That's not always the case, nor is it necessarily the most impactful or powerful thing that HNMR can do for us. Generally speaking, if we're looking at those splitting patterns and integrals and we can figure out where all the hydrogens belong and what's next to each hydrogen environment, we can start to figure out what the structure of the carbon chain actually looks like and possibly even figure out the position of functional groups as well. So the last thing that I want to look at today is Cnmr, and when we're recording results, all we need to do is record ppm shifts. So if we look at an example of Cnmr, we'll see that there aren't really any splitting patterns present. We just have single peaks that are at corresponding ppm shifts. And the reason for that, like we talked about in the previous video, is because Cnmr has really low resolution compared to HNMR. So the only thing that we can do, because there are no splitting patterns or integrals, is just look at ppm shifts. So similar to IR, we have a table of chemical shift data that can be used to try and identify different bond types and functional groups. And that's in our data sheet. Similar to HNMR, each peak that you see in a spectra is connected or related to particular carbon environments, and we determine carbon environments in a very similar way to the way that we determine hydrogen environments. So for example, in propan-1-ol, there are 3 different environments because every single carbon is bonded to a different set of things. Furthermore, not only are they bonded to a different set of things, but the carbons that they're attached to are completely different as well. In comparison though, propan-2-ol only has 2 carbon environments. Both of the outer carbons are CH3 groups. They are both bonded to 3 hydrogens. But even more than that, each carbon is bonded to the same type of carbon all the way along. So the carbon on the left is bonded to a carbon that's attached to an alcohol group and hydrogen, and then a CH3 group on the end. And the carbon on the right is bonded in exactly the same way, just in the reverse order. Again, it's the symmetry of this molecule which actually reduces the number of carbon environments. And as a result, propan 1-ol spectra will have 3 different peaks, and propan 2-ol spectra will only have 2 separate peaks. Our example here, we have an ester, and in this ester there are 4 different carbons. Now, there is absolutely no symmetry about this one. None of the carbons share the same environment, even the 2 on the end that are both CH3 groups. Reason being that the CH3 group on the left is bonded to essentially a carboxylic acid functional group, whereas the CH3 on the right is bonded to a CH2 group, meaning that those carbons, while similar, are completely different. We can even see that similarity in a lot of ways because the C1 and C4 carbons have very similar shifts, but they're not exactly the same. And using the shifts that are present, we can see that C4 matches the shift data here for carbon-carbon bonds, which is what we see between C4 and C3. For C1, which is bonded to a carbonyl group, we can see that with its shift just above 20, it matches the data that's here, a carbon bonded to a carbonyl group, which is good. For C3, we see a carbon bonded to oxygen, and having a shift of 60 matches the data that's here. Essentially, a carbon bonded to an ester is what we see. And then the last one, C2, is part of a carbonyl group, and we see that its shift matches the data that's down here for our esters. Note as well that the carbonyl groups for esters and acids and aldehydes and ketones are slightly different as well. That's really important to pay close attention to. So for Cnmr, we can use our ppm shift data to analyze each of the carbon environments and use that to start to identify different kinds of functional groups that might be present in the substance. Noting as well that we can look at the number of peaks and use that to identify the number of carbon environments present as well. Thank you very much, everyone. With the conclusion of this lesson, we've learned how to use different types of spectroscopy to identify unknown organic chemicals using a variety of different techniques. We're going to be moving in a slightly different direction going into a next set of lessons. We're going to be really focusing on the monitoring and management of the environment, and in particular, looking at ways to undertake some chemical testing to find the presence of inorganic contaminants. This isn't the last piece of spectroscopy that we will do in this topic, but it certainly is the last lesson on spectroscopy to identify organic chemicals. Further spectroscopy techniques that we will look at will be much more focused on determining concentrations in various substances. But until then, have a good one.